Welcome everyone to the 19th lecture in the lecture series on Circuit and System. I'm Nikhil Kumar Nigam from EEE Department, Delhi Technical Campus. In today's lecture, we will start with having a recap of what we discussed in the last lecture, and then we will move on to today's objective. In the last lecture, we were discussing about the circuit analysis using Laplace transform, and we will continue our discussion in this lecture also. We were discussing why the Laplace transformation. Up till now, we have discussed the circuit analysis in the time domain approach. That is, we will write the dynamic equations, which are generally in the form of integral differential equations. Integral differential equations. And in time domain, we used to solve these equations to find out the complementary function and the particular integral, thereby to find out the solution of the equation. Solution in time domain. The problem with this method was that we needed to solve integral differential equations, and which are very tedious task to solve. We have already seen that in the circuits where we involve the step analysis only, then the solution was very difficult. But if we involve even further complicated signals like sinusoidal signal or the exponential signals, the analysis may become further complex. And hence it is not a good choice to solve these integral differential equations in the time domain. But the good thing about the time domain analysis is that our mind can only respond or can only understand the time behavior. That is, if I want to understand or if I want to comment on the response of a system, that response of the system should be mentioned in the time domain only. So keeping this in mind, we invented, or the mathematicians invented, a method of Laplace transform, where using the Laplace transform, the integral differential equations are converted into linear algebraic equations. Linear algebraic equations in S domain. In S domain, that is, by the Laplace transformation, we are changing the domain of the system. We are changing the domain from time domain to the S domain. This S domain is generally called the frequency domain or complex frequency domain. The good thing is that in the S domain, we only have linear equations, and these can be very easily manipulated to get the answer. By manipulation, I mean partial fraction expansion. It means this: whatever the integral differential equation we have, we will apply the Laplace transform to convert them into linear algebraic equations, and to manipulate it, we will use partial expansion method. And after the partial expansion method, we will again apply the inverse Laplace transform to convert that into the time domain. So using the Laplace transformation, we will again get the response in the time domain, but we need to perform the transformation two times. In the first transformation, we will be converting the time domain into S domain, into the linear algebraic equations, and in the second transformation, we will be converting the S domain solution into the time domain solution using the inverse Laplace transformation. And before taking the inverse Laplace transform, we need to manipulate these algebraic equations, and the manipulation is done on the basis of partial fraction expansion. So in today's lecture, we will discuss about the partial fraction expansion. But before that, let us have a quick look of the property that we discussed in the last lecture. We discussed that if we have a function ft and I take the Laplace transform of it, then I will have a Laplace function f of s. Now the first property says that if I scale the function with a variable k, then the Laplace transformation will also be scaled by the same constant. That is, the scaling property says that if we are scaling the time domain function by a certain factor, then the Laplace domain function will also be scaled by the same factor. The additivity property says that suppose we have two time domain functions, f1 of t and f2 of t, and if I am adding them up, then the Laplace transform of the addition of these two will be equal to the Laplace transform of the addition of the Laplace transform of the two individual functions, f1 of s plus f2 of s. The third property we discussed about the time differentiation property. If instead of f of t we had f dash of t, then it will be equal to s time f of s minus f of 0 negative. That is, the Laplace domain of f of t will be multiplied with s, and a function and a constant is to be subtracted. This constant is the initial condition, that is the value of the function at t equal to 0. Now if we have further more derivatives, that is the derivative of nth order, say differentiation of this f of t with the order of n, then its differentiation then its Laplace will be equal to fs multiplied with s raised to power n minus s raised to power n minus 1 multiplied with the initial condition, then minus s n minus 2, f dash of initial condition, that is the initial condition of the first derivative, then the initial condition of second derivative, and so on. Further, we saw the time integration properties, that instead of f of t, if we have its integration, then the Laplace transform of it will be f of s divided by s. So from these two properties we can clearly see that differentiation can also be differentiation and integration both can be converted into simple linear forms. That is why we are preferring Laplace transformation, because it does not involve the integration and differentiation part. We will be having only the linear expression, and which can be solved very easily. Then we have frequency differentiation property. Say we have the function f of t, and if it is multiplied with t, then its derivative, then its Laplace transform will be the derivative of the f of s. That is, we now have the derivative in the s domain or the frequency domain. That is why it is termed as frequency differentiation property. Now, if we have f of t divided by t, this means in the s domain we will be having the integration of f of s ranging from 0 to infinity. Okay, then we have time shifting property, very important property. In this property we discussed that f of t minus a, if we have the f of t whose Laplace transform is f of s, then f of t minus a, see here this function is the shifted version of this. Then if I am doing the time shifting in the time domain, then in the s domain it will be multiplied with e raised to power minus s, where minus a is the factor by which the function has been shifted. See here, if it has been delayed, then it will be minus a, and if it is say prepondered, then it will be plus a here and plus a here. That is, the sign remains the same in the time shifting. Then we have frequency shifting property. In the frequency shifting property, we had when we have the function f of t and it is multiplied with e raised to power minus at, then the response would be, or the Laplace transform would be f of s plus a. That is, if we have multiplied e raised to power minus at, then negative of it will be added here. The negative of this function would be plus a, so it is added here. Now if we multiply it with e raised to power at, then negative of it will be minus a, and minus a will be added here, so it will be f of s minus a. So we can see that there is a shifting in frequency, so it is frequency shifting property. Okay. Next we have initial value theorem. If we want to find out the initial value of the given function in the time domain, then it will be equal to s times of f of s, where limit s tending to infinity. This will give us the initial value or the transient value of the function. Similarly, if I want to calculate the final value or the steady state value, then the final value or the steady state value of the function f of t will be equal to limit s tends to 0 s times fs. Now this will give us the steady state value. But this final value theorem is applicable for non-periodic functions only. If we have a periodic function, then this is not applicable. Then we discuss some the common Laplace transform of common signals. We discussed the Laplace transform of step signal. It was ut. Ut will have a Laplace transform of 1 by s. Similarly, the ramp function, ramp signal rt will have a Laplace transform of 1 by s square. Impulse signal delta t, this will have a Laplace transform of equal to 1. Exponential signal e raised to power minus at, it will be having a Laplace transform of s plus a. And similarly, if it is e raised to power at, then it will be 1 divided by s minus a. Similarly, if we have a sinusoidal signal, then the Laplace transform of sine omega t will be omega divided by s square plus omega square. And if it is a cos signal, then it will be cos omega t, and its Laplace transform will be s divided by s square plus omega square. Students generally get confused between the using or between these two formulas. Then I told you to remember the method to remember this formula. If we have s in the end here, say we do not have s here, then it will be omega in the numerator. If we had s in the end here, then s will be in the numerator. So remember this in the property, whichever trigonometric function has s in the end, sine and cos, in these only cos has s in the end, then this s will be there in the Laplace transform in the numerator. Similarly, we have sine hyperbolic signal, then sine hyperbolic omega t will be equal to omega divided by s square minus omega square, and cos hyperbolic omega means it will be s divided by s square minus omega square. Students generally also get confused between this cos hyperbolic and cos omega t formulas. So remember, with the introduction of h, it introduces minus signal here, minus sign here, otherwise it will be positive. So in today's lecture, let us move on to today's objective. We will discuss the partial fraction expansion method today. If we go back into the previous slide and let us see the Laplace transform of various signals, we will notice that all these Laplace transforms are in the form of numerator to denominator, numerator to denominator. It means this, whenever we are taking the Laplace transform, then it will always be a fractional function. Say we have f of s as a fractional function, which is equal to ns divided by ds, where n is the numerator polynomial in s and ds is the denominator polynomial in s. Now if I want to further solve it, then I need to write it in the lower order terms. If it is if say ds is a polynomial in s with degree say n, then the direct inverse transformation cannot be taken here. In order to take the inverse Laplace transform of this, we need to write this in the lower order terms. That is, we should write this in the form like n1s divided by d1s plus n2s divided by d2s plus n3s divided by d3s and so on, where the the condition is that n1 must have the degree of n1, I should rather say degree of n1 should be less than the degree of d1, degree of n2 should be less than the degree of d2 and so on. Also the degree, this expansion is possible, if the degree of numerator n is less than the degree of d, that is, this expansion is possible only if the numerator has lower degree than that of denominator. If in case the degree of numerator is greater than the degree of denominator, in that case we will first perform the division and then we will bring it to this condition where numerator will be less than the degree of denominator, and then we will use the partial fraction expansion. Also, with the partial fraction expansion, it is obvious that when we are expanding it into these forms, simpler forms, then obviously the degree of d1 or degree of d2 and so on must all be less than the degree of the given polynomial d. That is, these all must have the lower degrees than that of this. So in that case it will be termed as the partial fraction expansion. We will now look into the methods to calculate or to find out the ways of expressing or finding out these factors. Also, these n1, n2 and n3 up to so on, these are termed as the residue functions or the residues of d1, d2 and so on. These are termed the residues, and d1, d2, d3 are the factors of function or the polynomial ds. They must be the factor of ds. If they are not the factor of ds, then obviously this cannot be decomposed into the lower fractions. Let us consider the first case. Where fs is equal to ns divided by ds, and it is given that the degree of ns is greater than degree of ds. So if the degree of ns is greater than the degree of ds, we cannot apply partial fraction expansion. In that case, we will first divide this ns with ds to get or to write this function in the form, say, f of s equal to, say it is e of s plus n dash of s divided by ds. That is, after division I can write this as like this, where this is the quotient, this is the remainder and this is the divisor. Now if it is the remainder, then it is obvious the degree of n dash s must be less than the degree of ds. Now if its degree is less than the degree of ds, now we can apply partial fraction expansion here. So this was the first case where the degree of numerator was greater than the degree of denominator, and we learned whenever we encounter a case where the degree of numerator is greater than the degree of denominator, we will usually perform the division method first, followed by the partial fraction expansion. Let us discuss the second case, case 2, where we have f of s, where this is further equal to ns divided by ds, and it is mentioned that degree of ns is less than the degree of ds. As the degree of ns is less than the degree of ds, so obviously we can perform the partial fraction expansion. But in this also, let us say this ds can further be written as s minus d1, s minus d2, s minus d3, and so on up to s minus dn, where these all are the factors of this ds. In that case, we can decompose fs and we can write it as n1 divided by s minus d1 plus n2 divided by s minus d2 plus n3 divided by s minus d3 plus and so on up to nn divided by s minus dn, where this n1, n2, n3 and n4, nn are the residues of d1, d2, d3 and dn. And this s minus d is the factor of f of s minus d2 is also the factor of this, and likewise. Notice here all these terms are of first order. That means this ds should be able to be decomposed into the first order terms only, and only in that case we can write them like this. Then there is a residue theorem which enables us to calculate the values of n1, n2, n3 and nn, where the n1 can be calculated as n1 is equal to s minus d1, where we are calculating the residue of this d1, then n1 will be equal to s minus d1 into f of s, that is I will multiply this with this, and after their multiplication I will substitute s equal to d1, that is substituting this equal to 0 I will get s equal to d1. So I will get the value of n1. So let us similarly calculate the value of n2. n2 will be s minus d2 multiplied with f of s at s equal to d2 and so on. This particular function or this particular solution is known as the residue theorem. The method of calculating the residues is termed as the residue theorem, and this is applicable in this manner if and only if all the terms are in first order. So this is the case 2, where all the factors of this denominator ds are of first order. Let us now discuss the next case. We have case number 3rd, where f of s is equal to n of s divided by d of s, provided that degree of n of s is less than the degree of d of s, and further we can decompose ds into the factors like x minus d1, x minus d2, and along with the first order factors we have x minus dn square. That is, we have a factor which has a certain multiplicity, that is the order of this function or this factor is 2. What to do in that case? How to calculate the residues? In that case we can represent fs to be equal to, this will be n1 divided by x minus d1 plus n2 divided by x minus d2 plus and so on. This will continue if all these are of first order. Whenever we encounter a factor of higher order, then this will be changed. It will have a residue of let us generalize it. Say we have its multiplicity with the power of k. Let me write it, that it has a multiplicity with the power of k. Then the residue can be written as nn naught divided by x minus dn raised to the power k, plus then we will have another residue which will be nn1 divided by x minus dn with the lower order k minus 1. We had k here and we have k minus 1 here, and this will continue till we had n minus k, that is the kth residue for this vector, divided by x minus dn to the power k minus k. K minus k means it will be 0. I'm sorry, this should not be 0, in fact it should be 1. If it is 1, then the residue will be k minus 1. Okay, so this is how we will calculate the residues whenever we have a multiplicity of any factor. Now, how to calculate these residues? We have already seen the calculation of n1 because it is a residue of a simple factor. So now we will apply the residue theorem to find out these variables. So these residues, we have nn naught, that is the residue of the highest order term, nn naught, and this will be equal to x minus dn raised to the power k multiplied with the same function f of s. Sorry, I should not be having x, it should be s. It's my mistake, please. We should have s here, s. Please excuse my mistake. I was taking the reference from a second year mathematics books. That is why I have mistakenly written x over here. It should be s everywhere. Rather, I should write s. So now the residue of residue nn naught can be calculated by multiplying the highest order factor with f of s and then substituting s equal to dn. So at s equal to dn, this factor will yield the residue nn naught. Now, how to calculate the residue for lower order factors? The nn1, please see closely here, the nn1 can be calculated by finding out the derivative of this function. Derivative of this function will be derivative with respect to s minus dn raised to the power k f of s, and then substituting s equal to dn. If I am finding out the first derivative, it will give me the first residue of the lowest term, lower order term. Similarly, if I keep on calculating the derivatives, then nn2 will be d by ds square, that is I need to find out the double derivative of s minus dn k raised to power minus 1, sorry, not minus 1, it should be k only, f of s, and then substituting s equal to dn. So these are the formulas to calculate the residues when we have a multiplicity of a factor. Now let us discuss the another case. In this case, we have a fraction expansion f of s, which is equal to ns by ds, and it is further provided that the degree of numerator is less than the degree of denominator, and also the factors of ds are x, not x again, it should be s square plus say d1 square, s we have s minus d2, s minus d3 and so on. That is, in the factors of ds we have a second order term here. All others are the first order terms and there is no multiplicity, but we have a second order term here. In that case we can write this as, if I want to write this, I can write this as s minus j d1, s minus j d2, sorry, not d2, it should be d1 again, d1. That is, I can write this expression like this as plus, this should be plus, s minus j d1, s plus j d1. If I multiply with them together, I will again get this. So this can be written in the first order terms like this, and all other terms are of first order, s minus d2 and so on. That means using this I can write this expression as, in the expanded form I can write them as n1 divided by s minus j d1. That is, if n1 is the residue of j d1, then the residue of this would be n1 star, where n1 star is the complex conjugate of n1, divided by s plus j d1 plus n2 divided by s minus d2 plus n3 divided by s minus d3 and so on. That is, the things will remain same, only the thing is that s square plus d1 square, it should be written in this form first, and then we can expand this like this. And similarly the calculation of these n1 and n2 will not change. That is, the n1 will again be, n1 will be s minus j d1 times f of s, and I will substitute s equal to plus j d1. And if I further calculate n1 star, this I can calculate by calculating n1 and taking the complex conjugate of this, or I can use s plus j d1, because n1 star is the residue of this factor. So I will multiply this factor with f of s, and then I will substitute s equal to minus j d1. That is, equating this equal to 0, I will get s equal to minus j d1. So the solution from this will give me n1 star, and n2 and n3 can be further calculated in the similar way. That is, n2 will be s minus d2 into f of s at s equal to d2 and so on. So we need to remember all these partial fraction expansion methods in order to learn more about the use of Laplace into the electrical circuits. Let us now discuss the application of Laplace transform in the circuit analysis. Let us consider a resistive circuit first. I have a resistance, let me say I have this resistance which is connected across a voltage, time dependent voltage Vt, and due to this time dependent voltage a current It is flowing into it. Now this resistance is R. Now the relation between all these can be written as Vt equal to R times of It. Now we have this equation in the time domain. Let us transform this into the Laplace domain, taking Laplace transform both sides. I get. Now let me express this Vt, the Laplace transform of Vt, the Laplace transform of Vt as V of s. I will use a capital letter V, and similarly the Laplace transform of It to be equal to Laplace transform of It to be equal to capital I of s. Now taking the Laplace transform, I get V of s to be equal to R times of I of s. Now as R is a constant, so its Laplace transform will be R only. We all know that the Laplace transform of a constant remains the constant. So we have this equation. This is the Ohm's law in frequency domain. Now this equation is stating us that when voltage is converted into frequency domain, it becomes V of s. Current from time domain converted into frequency domain, it becomes I of s, and the resistance does not change. It means if a resistance is to be represented in the frequency domain, it will again be resistance only. Its property does not change if we refer it to the time domain or we refer it to the frequency domain. So resistance is resistance in both the cases, that is in the time domain as well as in the frequency domain. So now if I draw the frequency domain equivalent of this circuit, then using this equation I can draw that equivalent. That equivalent will be having a voltage of Vs flowing connected across a resistance R, and it will be causing a current Is to flow into it. So its Laplace domain equivalent will be a voltage source which is V of s. It will be connected across a resistance R, and a current I of s will now be flowing into the circuit. So this is the equivalent circuit in frequency domain. So the things that are changed, let us see. Vt has changed into V of s. It was a voltage source, it is still a voltage source here. The current It is changed into I of s. It was a time dependent current here. Over here it is a frequency dependent current, and if it is a resistance here, it is still a resistance here. So we can conclude from this that whenever we have a resistive circuit, all the time dependent variables are changed into the frequency dependent variables, but the resistance remains the same. If it is a resistance R here, then in the frequency domain it still will be acting like a resistance. That is, its property does not change when we convert it from time domain to frequency domain. So this is how we can convert a resistive circuit from time domain into frequency domain. So in the next lecture we will see the transformation of a inductive circuit, capacitive circuit, and the circuits with the combination of these elements RL, RC and RC, and we will use this Laplace transform to analyze and find out their solution. So that's it for this lecture. I hope you have learned something new from this lecture. So thank you so much for listening to the lecture. If you have any queries, you can mail me your queries at n.nigam@delhi-technical-campus.ac.in. You can WhatsApp me at this number, or we can discuss them in the tutorial sessions. Till then, take care, have a good health, bye bye.